Hello, this is Professor Huntington, and I'm going to explain a little bit about graphs, paths, and circuits. In this video, we are going to represent problems using graphs, and I'm going to talk about paths, circuits, and bridges. Let's define some of these things. So a graph is a finite set of points called vertices. The singular form is vertex, so if you have many, it's vertices. Also note that this is called nodes in other textbooks and videos. So nodes and vertices are the same. They're just the dots in the graph. Okay, so a graph is a finite set of points called vertices connected by line segments, not necessarily straight, and these are called edges, those line segments. You can think of edges as like a string, and being flexible, I think that helps to visualize the graph a little more abstractly. So think of edges as strings. One of the most famous problems in graph theory is the Königsberg bridge problem. So Königsberg was situated on both banks and two islands of the Pregel River. From the figure, we see that the sections of town were connected with a series of 7 bridges. Here's a map of those 7 bridges. And you could see here's a landmass, which could be represented with a vertex. Here's another one, here's another one, and here's another one. And then the bridges themselves can be represented with edges. And so we can create a graph to help us analyze this scenario a little better. And so the problem that they created, which was fun and it drew in visitors, is the townspeople wondered if one could walk through the town and cross all 7 bridges without crossing any of the bridges twice. So here we have the map again. And so I encourage you to pause the video and try to see if you can start anywhere on here and traverse through without crossing a bridge twice. Let's try together. We'll try A, start there, then we go to B, then from B we can go to D, and then we go there, and then we can go there. We can go back to the same vertex, we just can't traverse the same bridge twice. And then we can go back around here, and then here. Oh, see? Well, to traverse that last bridge, it looks like I'm going to have to traverse this one twice. So in that case, we got stuck. You could go back and look at the map again, and then try it yourself. I'm hoping you tried to find a way to traverse through all the bridges without traversing one bridge twice. And what you will see is it might help to view this as a graph, just a plain graph with vertices and edges. So that's how you could represent the Königsberg bridge problem. We can also represent many other things with a graph, like a floor plan. So imagine we have this floor plan of some fitness gym, and if you see here on the right could be a representation of that. So H in the center seems to be connected to the most. Okay, and we're going to talk about that in a little bit on about the degree of a vertex. And as we see, H probably has the most connection, so it will have the highest degree. Okay, so the degree of a vertex is the number of edges that connect to that vertex. A vertex with an even number of edges connected to it is an even vertex, and a vertex with an odd number of edges connected to it is an odd vertex. So let's take a look here. In the figure, vertices A and D are even and B and C are odd. Well, why is that? Because A has 2 edges connected to it, so it has a degree of 2. What about B? B has a degree of 3. And 3 is an odd number. So B is an odd vertex. Over here, C has 3 edges connected to it, so that's going to be an odd vertex. And then look at D. So we're actually going to count the loop also. So D has a degree of 4, and that's odd. So vertices A and D are even, and C and B are odd. Paths. A path is a sequence of adjacent vertices and edges connecting them. So you can go and traverse anywhere. So here's an example of one where you'd have C, then D, and A, and then B. So that's how you could represent that path. Okay, so C, D, A, B, as it said there. Paths. More about them. A path does not need to include every edge and every vertex of a graph. In addition, a path could include the same vertices and the same edges several times. For example, on the next slide, we can see a graph with 4 vertices. The path A, B, C, D, A, B, C, D, A, B, C. Okay, so going around, it's this one. So you can keep going around. That's also considered a path. Sometimes this is described differently in different textbooks and by different people. Some textbooks would call this more of a walk, and a path is one where you don't go back through the same vertex again. But for the sake of being general, a path and a walk are going to be the same. So it's just a path that you take. A circuit. It's good to think about, what does the word remind you of? Maybe a circle. Okay, that'll help you to remember this. So a circuit is a path that begins and ends at the same vertex. So we can start at A and then go to C, then B, then D, then A. And because we started and ended at the same vertex, this is called a circuit. You can think of other circuits in your life that you know about to help remind you that it's going to be a closed system and starts and ends at the same place. So think of an electrical circuit. That is going to be a flow of electrons that goes through, and it's like a circle. And maybe circuit training in the gym, you start and end at the same machine. And then trails that are circuits, so if you go out hiking, those are ones where you can go around and then you end up where you started, which helps if you park somewhere. Otherwise, you either have to go on that hiking trail to some point and then turn around and traverse like the same way, or you could, get a car to bring you back, or some other form of transportation to bring you back to the beginning. But I think you get the idea that a circuit could be helpful because it starts and ends in the same location. A graph is a connected graph if for any 2 vertices in the graph there is a path that connects them. So let's take a look at one. So this is considered connected because from any vertex here, let's say G, you can get to any other vertex through the graph. Sometimes it could be a long path, but at least you can get from any vertex in this graph to any other. Let's take a look at a disconnected one. So a disconnected graph is a graph that is not connected. So for example, this could be one graph, and so this is disconnected because if you are at A, you cannot get to C or B using this graph. And same for these 3 vertices over here, you cannot get to A. You could think of subway maps and train systems and maps as other examples of graphs. And so this could be maybe on an island, and then this is the subway route in some other region, and altogether they're considered one subway system, but you would say that these are disconnected routes. This is disconnected. Here's another example of a disconnected graph, because considering this whole thing, then if you start at B, you cannot get to F within this graph. And from, other ones as well. So you can see that it's disconnected. And this one is a little tricky because it looks like you can get from A to B, but you can't, because this is not a vertex right there. So this is also considered a disconnected graph. And A and I can't see it because I have my video there. A and D are connected, and B and C are connected, but the whole graph together is disconnected. A bridge is an edge that, if removed from a connected graph, would create a disconnected graph. And so here's an example of that. I think of bridges as being the most vulnerable part of a graph, so that if it were to break or something happened, then it would just make the whole thing break apart, okay, the whole graph. So yeah, if you remove that bridge, then A becomes disconnected from the rest. Here, this represents a bridge as well. That gets removed, and they're disconnected. And every edge in this case is a bridge.